Good. So if that's the case, so let's see how we can put things together, expanding the out of order scheduling we have done. And once we are done with this lecture, which mostly we will not be able to do by today, because we also need to rerun the example we have done last time, including this new stuff. But then if we're not done by today, Tuesday we will finish it. And then on the tutorial, as well as in the remaining lectures, I will try to solve more problems with you. I will stop technical topics and maybe cover more problems just to prepare for the final, given that our final is one of the earliest. And I have promised that I will raise more questions, so I will do so today or through the weekend. All the cash lectures are already on Avenue. The DRAM lectures, the reason that they were delayed is that some of the recordings, in fact, didn't go through. Team stopped during the lecture. But I have some old recordings from another lecture, so I will release these to you. And I have the same problem with out of order. That's one of the lectures not really very recorded, so I will see if I re-record. But I don't have the recording, the old recording of the out of order, so I will see what I'll have to do. But hopefully by Monday you will have all the recordings that you need. You will have more problem sets, and during next week we will solve more. So you prepare more for the final. Good. So what we have done so far is scoreboarding Tomasulo, and then we said for Tomasulo's algorithm, I'm using register renaming mainly to remove the non-fundamental dependencies, so right after read and right after write. Now, a problem that we discussed in few minutes in one of the lectures is without order execution, I have the problem of precise state. And I told you the problem right now is that if I allow instructions to finish and write to the register file out of order, I might have the problem that if I have an interrupt or I leave the pipeline and then come back into it, I must really make sure I keep the program order, because otherwise things are incorrect, right? If you have a flow of instructions and then with in order pipeline, if you basically had an interrupt in one of the instructions, it's very simple because you are sure, given the in order pipeline, whatever you have executed before has finished, and whatever is going to come into the future didn't start executing because everything is going in order. And if one instruction stalls, everyone is stalling. The problem with out of order is that that's not the case. If you put your pointer in any of the instruction, you are not really very sure which instruction did finish versus not, because I have reordered everything based on the readiness, right? So which means if I have an interrupt and I need to jump to another context and then come back, then, well, which instruction I need to start from, which one did finish, and which one didn't finish, so I have to repeat. This is called usually maintaining precise state, right? And we're going to discuss this. And then also how to do the write-read scheduling for out of order. The good thing is that we are trying to put everything together now. We have out of order scheduling. We refer into it as dynamic scheduling as well, and then superscalar, and then speculation. Speculation, you can think of it as I said before, it's one of the most general trends in computer architecture. One topic that we already discussed about speculation is branch prediction, right? It's a type of speculation, right? But there are in fact so many other types. Why we're bringing up these concepts together? Because in reality, modern machines are deploying all of them, from experiments, empirical results. Computer architects, both again industry and academia, found that these three concepts, in fact, play together very well to give you the maximum possible performance. First of all, if I want to increase my CBI beyond 1, well, the only option is I have superscalar, right? As we discussed in the superscalar lecture. But the challenges we faced in superscalar is that once you have multiple pipelines, dependency checks becomes right now quadratic, right? N squared. Like I have to do all the checks, all the bypassing logic between all the pipelines, which is very complex. And also limits the gains you obtain, yeah? Well, yeah, well, it's the other way around. It's been whether here we are discussing the problem or the solution. It's a good idea. So simply, this is a problem. IBC larger than 1 is what you're looking for, right? Because they are the opposite of each other. So here we are basically showing the problems, and here how we address them as solutions, right? So maybe I have said it the other way around. What I said is that we want to increase IBC beyond 1, which is also means I want to decrease CBI less than 1, right? That's so correct. But the style here is that there is a problem and we're looking for a solution. The problem is that CBI ideally, cycles per instruction, for an ideal pipeline is equal to 1, and we never even reach that 1. It's a little bit higher because of the hazards. And we said one solution for this is to add superscalar. Again, the problem with superscalar is that dependencies becomes way higher. How to solve dependencies to gain the performance again? Out of order scheduling or dynamic scheduling gave us a way by saying if there is an instruction that is stalling because of these dependencies, right now you don't lose the performance. Instead, pick another instruction that is ready, right? So out of order addresses some of the limitations or the dependencies or the hazards in the superscalar that prevents you from reaching closer to the ideal IBC that you're looking for. Good. And then even without order, read after write dependency is still a problem, right? All that like Tomasolo or scoreboarding or any out of order algorithm, in reality, there is no other way around than stalling or not stalling because you can do bypassing, but you have to address the read after write dependency because we said this is the fundamental dependency, right? With renaming, I eliminated write after write and write after read. But this one, there is no other way around because I'm waiting for a data and another instruction is calculating, right? But one way to handle this is if there is one instruction stalling in read after write, and remember, both Tomasolo and scoreboarding were stalling read after write in the issue stage, right? So I dispatch it, I locate the units, the hardware, but then when I try to issue it, which means read the register values, if the register values are not ready, I have to stall. This is why I'm stalling at the issue stage. One way to overcome the performance penalty of this is that people usually use a large instruction window. What is a large instruction window? Simply increase the buffer size of the instruction buffer or the reorder buffer. And again, in Lab 2, which came way earlier than these discussions, simply we played around with the size of ROB. And we see by increasing the size of ROB, the performance is increasing. The reason for this is especially for out of order. In order, it doesn't really matter. The reason for out of order is increasing the performance is that you are giving the hardware more visibility into more instructions. So if there is a stall because of dependency, you are able to pick another independent instruction. So the more visibility I have for instructions, the more flexible the decision I can come up with, which means it's more ideal. Make sense? So we will overcome some of the reorder dependencies or their impact on performance by increasing the instruction window. Definitely here there is an area trade-off, right? You cannot really make it, 4K reorder buffer, right? So it's an area performance trade-off. And then another problem that we had in order and also in out of order, we didn't discuss much in out of order, but if you have branches, the problem with branching is that, well, this is a structure, this is the control hazard. I still either need to flush the pipeline if I mispredict, right? Or I need to stall if I don't have any branch prediction. But we found that the problem branch can be solved by really having branch prediction that is accurate, right? You add a complex branch predictor, and again, this was the topic for Lab 2 as well, right? Through BTB and branch history table, you are able to increase the performance by predicting the branches. Good. So by combining all these concepts together, branch prediction, a large reorder buffer or instruction buffer, out of order scheduling, and superscalar, which all exist in any of the machines you have right now, even like in mobile phones nowadays, is that you are able to increase the performance as much as you can for a single core. Good. So now there is one big problem. Is there any question in this slide? So you see how all of these come together right now? Good. So some of the data hazards I addressed by a larger instruction window and out of order scheduling, right after write and right after read completely eliminated by register renaming. Structure hazard, well, superscalar solving partially structure hazard because you replicate function units, right? And you increase beyond one IBC. And out of order scheduling allowing you to increase the performance to address also the hazards. Good. So now there is one big problem with all of this. Like I guess it seems like a utopia topic that we're able to achieve the ideal IBC, but it's in reality that's never the case. And one big problem related to all these topics together is what we call maintaining precise state or exceptions, right? What do we mean by exceptions? Usually, and relating this to something that you know very well from your embedded interfacing course, and in 4DS, we have a lot of detailed discussion in the lab and the lecture about this. If you are executing a normal user program task, right? Any program, including, for example, the assembly code we have in past lecture. At one point, nothing, this is your context, right? This is what you control. But the machine you are accessing, in fact, also have I/O devices, for example, right? Like in your laptop, you have the mouse or the touch screen. So the user or the external wallet might, in fact, interrupt your normal user program flow and take the processor to do something else, right? This something else, for example, can be the interrupt in embedded systems, right? So generally, I'm calling this an exception, not an interrupt, for a reason that will come into it in the next slide, because exception is a more general concept. But the idea is that while I'm executing, at one point, an exception happens. I must jump context to execute something else, right? And then this something else, once I'm done, I will return from exception. The problem right now is where to return. If I'm returning to the exact same instruction that I was executing with the one after, which is normally the case, then as I said at the beginning of the lecture, if this is in order pipeline, great, no problem, because all of this has already finished. All of this hasn't started. And if it was started, I just flushed the pipeline, so I have to start from the beginning. But if this was out of order scheduling, you must be seeing the problem right now, is that this instruction might not have executed. This one might have already finished. So if I'm starting from here, how do I know which one finished versus not? Right? It's a big problem. Good. Great. So do you see the problem? Makes sense? Okay. So there are these exceptions that you said is a general concept. In fact, they are caused by two different things. One of them is external to the program, which is what I used because this is what you knew from before, what I used to explain the concept to you. And the other one is, in fact, within the user program context itself. The first one is through interrupts. So they are coming externally from the system. These are external exceptions, right? So if I have an external event like a network packet, a keyboard access, disk I/O timer, whatever it is, and then we call it asynchronous because simply the reason for the interrupt has nothing to do at all with the program itself, right? It's completely external to my program. Good. And may be handled between instructions and can come at any time, completely asynchronous to my execution. Traps, on the other hand, and sometimes in computer arithmetic, these are called flags. Usually, they are caused by internal events of my execution of a program. For example, I might have an addition overflow, divide by zero exception, right? Those kind of things that might happen because of execution itself. If you open any ISA document, RISC-V, ARM, whatever it is, they have dedicated chapters to, sometimes they call it traps, sometimes they call it flags. So simply, how do you handle events that are incorrect? For example, you are adding and you are having an overflow for the adder because the result of the addition is larger than the register itself. Like just a little bit of background here. Assume, for example, the MIPS machine we had, a 32-bit machine. If I'm adding 32 bits to 32 bits, what would be the result in general? 33 bits, right? But my registers are only 32. So if really the 33th bit has a value, it has 1, that means this is an overflow, right? So the carry of the last bit is in fact the overflow, which means the result cannot be really stored in a 32-bit register, right? So the ISA tells you how to handle addition overflow, for example. If you are dividing by 0, example, or if the result of any arithmetic operation is incorrect or beyond the limit, right? All of these things are called traps. The traps, unlike interrupts, they happen because of the program context, and this is why they are synchronous to the program, right? They are a result of an instruction execution. And then this condition must be remedied by the handler or by the hardware itself. What to do? For example, do I set a flag bit to the user? Do I write to a certain register a certain value? What do I do, right? I mean, aside from this distinction, both are handled equally from the exception handling point of view, right? So these two, regardless of whether they are from the program or external to the program, these still cause exceptions. You still leave the larger context to do something else, and hence you need to handle them, right? Which one you imagine might be easier to handle or have less problem on handling? Yeah, the traps. Yeah, why that's the case? Yeah, so first of all, they happen because of me as a hardware circuitry, and I can also add another logic to really remedy them. For that reason, in fact, they are easier to handle. and I don't need to completely leave my context to go somewhere else. While for the interrupts, I completely leave that part, go to execute a completely different piece of code, another task, do something else, and then come back, right? So these ones are way harder to handle. Now, why? Okay, so we kind of discussed precise exceptions. We call here precise interrupts because interrupts are the real problem. But then why precise interrupts are related to out of order, I explained to you, correct? But why precise interrupts might be, in fact, related to speculation as well. Because if you think about speculation, which is the only speculation thing we had so far is in reality the branch prediction, right? You still have the same problem, right? In fact, branch prediction is nothing other than a small form of exception. Because what do I do for a branch? You leave your current context and you jump somewhere else, execute another instruction, right? But the point is that because you speculate, you might turn out to be wrong. So in that case, you need to flush and you need to bring the correct instruction, right? So you need to address the branching in a way that is pretty much similar to how you would address an exception. Because if you go to the exception here, in the very high level, before we delve into any detail, how do I really solve that problem for out of order? Any suggestion? Like think about, we said in order is no problem. First of all, in order, how do I handle it for in order? Yeah.
Go back to the same location.
Yeah, but then before I jump for in order, because this is pipelining, I still have instructions in flight. What do I do before I
like
flush them? Exactly. Thank you. So what I would do for in order, I flush the ones that didn't finish. The ones that finished, that's great because this is permanent state, and then I jump there. Yeah.
I think for out of order, you just redo all the ones that were in the buffer.
Good.
Then you all those.
Yeah, but what about the ones, for example, if I redo the ones that are in the buffer, and these ones in the buffer that might be this one, this one, and this one, and this one, while I've already retired this one.
Redo them all in the buffer, like starting from the
Yeah, great. So that's okay. This is the thought flow that I would like to elaborate a little bit more on. So if we do that, and then I redo them all, this one, because it finished, well, first of all, that's logical. It's because it finished, it wrote to the register file, so it has modified something, right? So the whole problem about exception is permanent state, right? You see that? If an instruction didn't write anything to a permanent state, then well, just flush it, don't care about it, or redo it because it doesn't really matter, right? Because it was in flight. The problem is I cannot really redo completely because it wrote to the register file. So what to do? First of all, when we say permanent state, in our control flow that we had throughout the course, what are the locations, the modules that in fact maintain permanent state in my pipeline? Permanent state means you have really written something permanently, like this instruction retires, its effect has been done in the system. I cannot, for example, I cannot say I just flush it because its impact has already happened. Register file, thank you so much. That's one of the most important. There is another one that is a little bit implicit. There are some instructions that in fact their permanent state is not in the register file, but instead is in memory, right? Great. So these are the two that are really maintaining permanent states, right? So as far as an instruction didn't write to the register file or to the memory, I'm good. I'll just flush it. I will jump, do the exception. When I come back, I redo it. Good. So now our problem with out of order is that as far up until now, what we discussed is that we allow instructions to write to the register file out of order, right? We allow them to update the write back register without the order of execution. Good. Why did we do this? Because we wanted other instructions to use this data, like to basically move forward in the pipeline. So the fundamental problem is that we are combining two things together. The result of the instruction and permanently writing it with a permanent state place, which is register file or the memory. Yeah.
Where we talked about like the write back buffer.
Yeah.
Would that be on the same order of the length, so you could like bring those values back?
Yeah, exactly. Thank you. So that's one of the. We will see that this is in fact one of the solutions. Yeah. Well, that's a good catch. Thank you. I would say this is maybe a bonus mark. So send me your email. Yeah, it's a good one. So simply at one point we discussed very briefly that there is something like a load store buffer or a write back buffer where we maintain the data of the write, right? By adding that buffer in the middle, you prevent the store from writing permanently to the memory. And for that reason, if in fact you flush it, well, I can still retrieve the original state, right? So we'll see that we are in fact going to use the reorder buffer for all instructions and that write back buffer or store buffer for the memory instructions to keep the intermediate data. And then we call it right now retire. So what we have done is we split the write back stage into two different stages because we want to do two different things. The first one is we propagate the result of the execution because we don't want to stall the pipeline, but we don't write to the permanent state. We don't write to the register file or to the memory except in order. Why I'm doing this? Well, because if you have an exception, right now everything is handled as if it's an in-order pipeline. Whoever has written to the register file, great, retire it. Whoever didn't write, flush it and start from the beginning. Make sense? So is the intuition clear right now? What are we doing? Good. So right now we split the write back stage into two, a one that we call complete and a one we call retire. The complete one will keep the result of the instruction in the reorder buffer instead of the register file temporarily, so it's an intermediate location, and you only retire instructions in order. What does it mean to retire instructions in order? You simply go through your reorder buffer and then you pick the one that is on the top. And if it's not ready to retire, everything else stays as is. Good. In reality, those of you that went through Maxim code for out of order scheduling, this is exactly what Maxim is doing, right? Maxim or any out of order, reasonable out of order implementation would insert instructions to the reorder buffer in order, would take them out of the reorder buffer, and take them out doesn't mean remove them, but just basically pick a one to schedule, send it to the execution completely out of order to improve performance, but only pop them out of the reorder buffer or remove them or retire them from the reorder buffer in order as well. Good. So we fetch in order, we retire in order, but in the middle we execute out of order. This is the trick how out of order is increasing performance while solving the problem of precise state. Questions? Good. So right now by splitting the write back state into two, complete and retire. For the complete, what I do is I complete all the results are written to the reorder buffer out of order. And I also broadcast, or if I bypass, for example, into Masulu, send it to all the other instructions, allowing them to execute out of order. While the retire stage, sometimes called commit or graduate, commit is the very common name in Intel, retire is what is being called in Maxim. Simply what you do is you take the result out of the reorder buffer and write it permanently into the permanent location, whether it's the memory or the register file, and this only happens in order. Right? And because this is in order, if there is a hazard, you have to stall. If there's an exception, you will jump and come back and then do it later on. Okay, so right now looking into the reorder buffer, the problem is solved for writing data to the register file. But the problem, as we said, also happens for memory instructions, especially stores, because loads don't stay well. Load instruction does change the permanent state of the register file, because I'm taking something to the memory, writing it into a register. While store is the only instruction that its permanent state is written to the memory, right? So this problem is in fact pertains to the store instruction. And I want to do something similar to the reorder buffer. This is what we call memory ordering buffer. Here I'm using a name that is a little bit abstract because again, people name it different things. Like previously we called it a write back buffer. And we also mentioned that it can be called store buffer, a load store queue, LSQ, which is the most common name in modern machines, store queue only. So it has multiple names, similar to the reorder buffer, right? Different companies name the same thing, different things based on the low-level detail implementation. But at the end of the day, it's a buffer similar to the reorder buffer, but it's used to maintain the intermediate results of the store operation. Good. So the store instruction writes into it. And I only retire the instruction if it simply writes to the permanent memory state. Good. And something we mentioned also when we talked about this write buffer is because we need to maintain consistency between loads and stores. If I have a load operation, I cannot really go directly to the cache, right? I have to check first the memory ordering buffer to see if my result is there, and if it's there, I pick it from there, right? Because if the store is writing to this one, while the load is going to bring data from the cache will have a stale date, right? Wrong date. That's incorrect. So you must first check your store buffer to see if there is any data that matches your address, and if so, you read it from there. Otherwise, you basically go to the cache. Good. So right now, putting it all together and I'll stop in this slide, and then hopefully on Tuesday we run through the example. This is what is called Intel B6 architecture, which is mainly what was in Pentium Brew families. But it's a little bit of simplification. What we have is we had our usual control flow. Remember, when we went out of order, we split the decode into dispatch and issue. Right now, we are splitting the write back into commit and retire. And then simply, we call it commit or complete or retire. And then we are using the instead of really writing to the register file, I'm writing to the reorder buffer. And then I'm only reading from the reorder buffer in order to write to the register file. So this is the retire stage, basically, right? That's how you retire. And the same thing would happen for the memory instructions. I store to the memory ordering buffer, and then only take out of the memory ordering buffer in order. And simply loads would have to check the memory ordering buffer first. If the data is there, you take it. If not, then you take it from the cache. Good. So let's stop here and we continue next time.